let's consider how the ansys solver will solve our mathematical model for us using the finite element method. And in this discussion, I will invoke concepts that we looked at in the big ideas in FEA. So I'm moving from talking about the mathematical model. So we know that our mathematical model is a boundary value problem. So I'm moving from talking about that to talking about the numerical solution strategy. So we have to divide the domain into elements and nodes. So we have a rectangular domain here, and we divide it into 9 little chunks. Each little chunk is called an element. So here I've highlighted one element. And the corners would be, I would call them the nodes. So I'll say these are the nodes. By the way, when we are in the ansys solver, it will also put in the mid-side nodes. We'll get to that when we are in ansys. For now, let's think of the nodes as just the corners of each element. And then we reduce the problem to determining temperature only at the nodes. Here I have 16 nodes, 4 times, 4 rows of these. So I have 16 nodes. So I'm going from determining temperature everywhere, so needing to determine a 2-dimensional function, to determining 16 temperature values. And that's a big simplification, and that's the advantage of discretization. And to use polynomial interpolation to relate temperature within an element to the nodal temperatures. If I want to know what's the temperature there, I would interpolate between these 4 values. In the 1D case, we were interpolating along a line. Now we have to interpolate within an area. So the interpolation is more complicated. It'll be a bilinear interpolation in this case, but the idea is the same. I think of this as, this value is a weighted average of these 4 values, and the weights for each of these values is given by the so-called shape function, for those of you who have seen shape functions. And now that we know that we need to determine only a discrete number of values, let's think about how the solver will determine those discrete values of temperature.